Alright, time to look at some doubly linked list source code. This is part 2 of 2 in the linked list series. So the link for the source code can be found on GitHub at github.com/williamfiza/data-structures. Please star this repository if you find the source code helpful so that others may also find it. And also make sure you watch the first part of the linked list series before continuing. Here we are in the source code. We're looking at the implementation of a doubly linked list in Java. So first, notice that I have declared a few instance variables. So we are keeping track of the size of the linked list as well as what the head and the tail currently are. To begin with, the head and the tail are null, meaning linked list is empty. Furthermore, we will be using this internal node class quite excessively because it contains the data for our nodes, and it also contains the previous and next pointers for each node, since this is a doubly linked list. So we have one constructor for the node, namely the data and the previous and the next pointers themselves. We need both, otherwise we can't do much. So this first method I have declared here is to clear the list. It does so in linear time by going through all the elements and deallocating them one at a time. It deallocates them by setting them equal to null. So we start a traverser at the head, we loop while the traverser is not equal to null, meaning there are still elements in the list, and then we do our deallocation business. And at the end, we set the size equal to 0 and reset the head and the tail. Perfect. These size and empty methods are pretty self-explanatory. Get the size and check if the size of our linked list is empty. Okay. So here I have a public method to add an element. By default, we're going to append to the end of the linked list or at the tail. But I also support adding to the beginning of the linked list. So how we do this, if this is the first element, aka the list is empty, then we set the head and the tail to be equal to the new node, which has, if you can see here, both previous and next pointers set to null. Otherwise, if the list is not empty, then we say the head's previous pointer is equal to this new node. And then we set the head pointer to be whatever head's previous is. So we back up the pointer in a sense, and we also don't forget to increment the size. A very similar thing is done when we want to add to the tail of the linked list, except we're moving the tail pointer around. Okay, let's move to peek. So peeking is just looking at either the element at the beginning of the linked list or at the end of the linked list. And we throw a runtime exception if the list is empty, because it doesn't make sense to peek an empty list. Okay, now we get to the first more complex method, which is remove first. So this is if we want to remove the head of the linked list. So we can't do much if the list is empty. Otherwise, we get the data, we extract the data at the head, and then move the head pointer forward. We decrease the size by 1. So if the list is empty, we set the tail to be null as well. So both the head and the tail are now null. Otherwise, we deallocate the memory of the previous node that we just removed. This is especially important if you're in C or C++. Make sure to free or delete your pointers. Then at the end, we return the data. A very similar thing is done for last, except we're using the tail this time to remove from the tail of the linked list and not the head. Okay, and here's a generic method to remove an arbitrary node. Remark that I set this to private because the node class itself is private, so the user shouldn't have access to the node. That's just something we're using internally inside the linked list data structure to manage the list. So if the node that we're removing is either at the head or the tail, detect that and call our methods either remove first or remove last. Otherwise, we know we're somewhere in the middle of the linked list. And if we are, we make the pointers adjacent to our current node equal to each other. So we're effectively skipping over the current node. And then, of course, don't forget to clean up your memory and return the data. So we have to temporarily store the data, of course, before we delete the node. Otherwise, we've deleted the node and the data is already gone. Now, suppose we want to remove a node at a particular index in our linked list. Yes, we can do this. Even though our nodes are not explicitly indexed, we can pretend that they are. So first check that the index is valid, otherwise throw in a legal argument exception. So here we are trying to be a bit smarter than just naively going through the linked list. Either we're going to start searching from the front of the linked list to find our index, or from the back, depending on if the index is closer to the front or to the back, although this method remains linear. So for the remove method, we want to be able to remove an arbitrary value from our linked list, which is object. So we're going to also support searching for null values in case someone decided that the value of the node should be null. That's fine. So we check that special case. Otherwise, we traverse through the linked list until we find a null element and then remove that node and return true. We return true if we've actually found the element we want to remove. Otherwise, we return false down here. In this else statement, we search for the element we want to remove. We use the dot equals method to check if we found the element. If so, remove that node and return true. Okay, here we have a related method, which is index of. So this is not remove at an index or remove a value, but get whatever index this object is at. Again, supports searching for null, so even if our value is null, we'll just return the first place we find a null element. So again, traverse the linked list. Otherwise, search for a non-null element, and also increment the index as we go. We can use the index of for our method contains to check if an element is contained within a linked list, because we return -1 if the element is not found. Something that's useful sometimes is to have an iterator for a linked list. This is also trivial to implement. Just start a pointer, traverse at the head, and traverse until you reach the end. Notice I'm not checking for concurrent modification error, but if you want to, it's pretty easy to do that. And lastly, at the very bottom, we have the toString method to print a string, or to get rather a string representation of our linked list. And that's it for the linked list. So pretty straightforward stuff, but there's a lot of pointers flying around. So if you're confused about a particular part of the algorithm, look at it in more details or comment below. I'll get to you when I have time.